Alrighty, folks, let's pick up with another problem. This is example number 5 on your, this is the 3.11 notes. So I encourage you to, if you're just looking at this problem for the first time, pause the video, try to draw a picture of the problem, and maybe even take a shot at the answer. Go ahead and try this, and then we'll resume here in a moment. Okay. So when I look at this, it seems to me the picture might look something like this. We've got a boat. Forgive my poor illustration skills. We've got a boat, and the boat is being towed into shore to a dock. That the dock sets 1 meter higher than the bow of the boat. Okay. So we're told that a pulley passing, let's see, there's a pulley up here, and it is reeling the boat in at a rate of 1 meter per second. Okay, so here's the question: what's changing at 1 meter per second? Is it this distance right here, or is it this distance right here, or is it this distance right here? What is changing at 1 meter per second? Think about that. So it turns out that what's changing at 1 meter per second is the rope length, right? Because it is the rope that is being pulled in at that particular rate. So notice that we formed a nice little right triangle here. So if we wanted to, we could go ahead and label this by the sides A, B, and let's go ahead and we'll call that C, I guess. And so when I'm telling you that the rope is being pulled in at a rate of 1 meter per second, that's a statement about how C is changing. We are told that dC dt is equal to, and I'd like to, well, we'll go ahead and make this a negative, that it's decreasing, that the length of C is decreasing at a rate of 1 meter per second. And so the question is how much faster, or how quickly is the boat approaching the dock when that happens? Now these numbers in this particular problem aren't that exciting, but you can see that this is a real world problem. If you may think that you're pulling this boat in very, very slowly, but it might turn out that because of this difference in height, because of this hypotenuse here, that as the boat gets closer and closer to the dock, to compensate for a 1 meter per second change in the rope length, the boat might end up going very, very fast, and you might actually run into trouble here. Like I said, in this problem, the numbers won't get too outrageous, but that's something to consider. Okay, so now we're ready to tackle this question. Remember that our basic procedure for tackling these problems involves, first, I guess, every time I've drawn a picture, so maybe you should draw a picture, but then trying to find a formula that relates all of the quantities together. Now be careful, at this point I'm talking about the quantities, I'm not talking about the rates of change. We will obtain the rates of change when we differentiate both sides. What I'm interested in is a formula that would relate these quantities here together. And so we're going to use a version of the Pythagorean Theorem, not just a version, the Pythagorean Theorem. Sorry, that was kind of silly to say. This says that a squared plus b squared is equal to c squared. Okay. So now we're going to go ahead and we found the formula, and we differentiate both sides with respect to whom? With respect to the variable t. Okay. So this gives us 2a times, here I'm just going to start using the prime notation, I think we've got it, times 2b times b prime is equal to 2c times c prime. Okay. Well, of these quantities, is there anything we can say to begin with? Well, let's just look at this. This is the length, the distance the boat is from the dock, right? And this is the current length of the rope, and this is the height between the where the boat will eventually dock and the height of the dock. And then we have our rates of change. So we have these three rates of change here. We have a prime, b prime, and c prime. We know what c prime is, right? C prime tells us how the hypotenuse is changing, and we know that that's decreasing at 1 meters per second from the given statement up here. So we know how c prime is changing. We don't know a prime, and that's precisely what we were asked to find. What is dA dt? How fast is the boat approaching the dock? Okay. There's one other derivative in here, dB dt. What is dB dt? How does b change with t? I want you to think about that for a second. So dB dt would represent a change in the dock height relational to the boat. Well, that dock hopefully isn't changing, and the boat's height isn't above the water, hopefully isn't changing. So what should be dB dt? We have that dB dt, or b prime as I've written it, should be 0. So that means we can greatly simplify this problem. We get that 2a times a prime is equal to 2c times c prime, and we want to know what a prime is, so let's divide everything over. We get 2c times c prime all over 2a, or that a prime is equal to c times c prime over a. Okay. Well, I think we're ready to start plugging in what we know. We want to know what dA dt is. Here I'll return to Leibniz's notation. We know that c, well, we don't know what c is. We know that the boat is currently 8 feet from the dock, right? So if the boat is currently 8 feet from the dock, let's go ahead and, although we have a triangle here, let's look at this specific instance. Here is the boat, here is the height of the dock, and here's where they have co-equal height. And we're told that the boat is a distance of 8 feet from the dock. We know that this, per our earlier discussion, is always 1 foot. Right? That's a fixed. Oh, do I have a mistake here? Yeah, I used the words feet, and I should have been using meters there. So anytime in the previous few minutes that I've said feet, I meant to use meters. Okay. And so then what is this quantity right here? Well, we could go ahead and use the Pythagorean Theorem on this, right? So this would be equal to, so C is this quantity, and here we have that C is equal to the square root of 8 squared plus 1 squared, or that C is equal to the square root of 65. Okay. So this was the one specific instance that we were interested in, and that's going to help us calculate the dA dt. So we have the square root of 65 times c prime. What is c prime? Well, c prime is 1. This boat is being reeled in at a constant 1 meter per second. I'll go ahead and put that there. All divided by a, and what was a? 8 is this 8 meters. Put a meters there as well. So we've got c times c prime divided by a, and when everything clears, we get the square root of 65 over 8 meters per second. And I know that this isn't too exciting of a result, and maybe one day I'll go back and change all these numbers so it's a little more drastic, but notice that the boat is traveling faster than 1 meter per second as it gets closer and closer to the dock. So the closer to the dock, the faster the boat will have to travel in order to keep up with the rate of change in the hypotenuse of that triangle. So if you were moving large equipment, that would definitely be something you'd want to be aware of, because a boat traveling at one speed has way different momentum than a boat traveling at another speed. So this was a challenging problem. I encourage you to maybe watch the video a second time and then work some similar homework examples. But the key here was recognizing that the formula that would relate all these together was the Pythagorean theorem, and then we proceeded from there. I hope this was helpful.